My name is Peyton Holston, and this is my video presentation for Lab 1. This lab stems from Newton's second law of motion, which states that the net force acting upon an object is equal to that object's change in momentum over a given time period. From this equation, and through a bit of clever algebra, we can reach the velocity and position update equations, which can tell you the final velocity and final position of a given object. This lab centers around testing the real-world applicability of Newton's second law of motion and the physical idea of constant velocity. This is important because through this law, we can extract explanations of observed motion as well as predict future motion. The procedure of this lab consisted of a real-world and computer model component. In the real-world component of the lab, I rolled a roll of tissue across a generally flat surface and tracked the motion to extract motion data. Here you can see the clip of the tracked motion of the tissue roll as it moves across the floor. From this, I was able to extract the displacement at given time intervals, allowing me to plot the position of the tissue roll relative to its starting position over time, as you can see on the graph. Given that both the change in position and time were known, I was able to further calculate the velocity over different time intervals. The second component of the lab consisted of creating a computer model of the real-world motion I recorded. Beginning first by initializing the mass of the ball, which in this particular model is generally irrelevant given that velocity is constant, which I'll explain more later. Next, I initialized the object's initial position and velocity as vectors with values given by my real-world model. Next, the starting time was initialized as well as the length of each increment of time. The next portion of the computer model was the calculation loop, which models the passage of time. The while loop, which tells the program how long to run, was given an upper bound identical to the length of my recorded clip from the tracker model. Given that velocity is constant, the vector describing the net forces acting upon the object was set to 0, not due to an assumed absence of forces, but more so the assumption that the forces would sum to 0. This shows why the true mass of the ball would be relatively unimportant to the model, because regardless, the value of the net force divided by mass would always equal 0, given that the mass was a non-zero number. Next, the ball's velocity was calculated using the velocity update equation mentioned previously. And the ball's position was calculated due to the position update formula, which was also mentioned previously. Finally, the time was incremented with the given parameter initialized earlier in the program. From the data given by the model, the position of the ball could be plotted over time. In addition, the velocity, which is seen here, can also be calculated over time from the position over time data. Now that we have collected this data, we can compare the two models to see if any differences arise. From the position versus time graphs of both models, we can see that for a majority of the time, the two models appear to have the same or similar slopes. However, as the time progresses, we can see that the slope of the real-world model begins to decrease. This decrease in slope is more apparent in the velocity versus time graph, as the velocity, the slope of the position versus time graph, of the real-world model begins to decrease and trend downwards. This tells us that there must be an imbalance of forces acting upon the object as it moves across the floor. Whether those forces are friction, air resistance, gravitation, or other forces, there must be some imbalance of forces to create a net force slowing down the object. However, the magnitude and number of these forces is unknown. If I were to flip the axes about the y-axis, the position versus time graph would maintain the same magnitude of slope. However, the slope would now appear negative as the ball would be traveling in the negative x direction. This relates directly to the velocity, making the velocity negative because the velocity is simply the slope of the position versus time graph. Also, as stated previously, there is no way of knowing the number of forces acting on the object at any given time, only the magnitude of the sum of the forces which show themselves through the net force. Finally, to close, in further experimentation to gain a more accurate representation of constant velocity in the real world, the experiment could be repeated on a near frictionless surface with a more regularly shaped cylinder or ball to maintain balance in the motion. These two would lead to a lower net force acting upon the object as it travels for an extended period of time. I hope you have enjoyed my presentation, and thank you for watching.